Good morning. Here we are again. As for questions for retakes of midterm, blah, blah, blah. Attendance, people. And secondly, if you read in the autos, you had to apply by the end of Saturday. Too late. And those who have not attended lectures for months, you have already failed. Your study agreement, which you signed when you enrolled in RTU, says if 2 months the student has attendance below 50%, the credit points are not counted for this course. So it's your own problem. Sorry. That's it. Now to mathematics. I'll switch off the camera and let's move on to mathematics. You cannot at the moment, you cannot. I don't have time to deal with lazy people. Absolutely not. Okay, so first of all, let's have a look at what we did last time. So we looked at the second order derivative, and we had some rules about the second order derivative. That is, if the second order derivative was positive on some segment AB, that actually meant that the graph is concave up, that is going upwards, maybe going downwards, but the concavity is up. So this shape of graph is called concave up or concave upwards. Or convex. Sometimes we also say convex. And then if the second order derivative is less than 0, negative on some segment, then we had the cavity, like concavity, the cavity going downwards. So it could be decreasing, could be increasing, could be both. So it's called concave down, or concave downwards, or we can sometimes say, simply concave, because it looks like a cave, you see, like an entrance to the cave. So we can say also concave and convex. So concave is the same as concave down, convex is the same as concave up. And then, of course, we had the next, we had this one more thing that I guess I didn't put it there. So if we have a point, and on the left of this point, the concavity is one way, say it's concave up, for instance, and then to the right, the concavity is the other way. In other words, the points where the sign of derivative change, the direction of concavity changes, are called inflection points. Inflection points, or we can also, flexion, not fection, inflection, another spelling, CT, without X, but with CT, inflection points. The inflection point is where the concavity, the direction of the concavity changes. For example, to the left, concave up, to the right, concave down, or the other way around. On the right-hand side, it's perhaps concave downwards, and then after the inflection point on the right, it becomes concave upwards. These points are called inflection points. The absolute necessity for inflection point is different signs of second derivative on both sides. That's what is important. So this was the theoretical part in the end of our lecture last time, for which we did not have much time because we were talking about optimization. And now second derivative to find the inflection, point. This, I already gave you a hint about this exercise. So using the second derivative to find the inflection point, perhaps I solved it to some extent. So the first derivative of this function, see the first term x times e to the power 2x is a product. So we can deal with it using the product rule. X differentiated is 1 times e to the power 2x not differentiated plus x not differentiated times e to power 2x differentiated, and that is the same e to power 2x times the derivative of 2x, of course. And of course, one derivative is 0. So in this case, we can take the exponential function e to power 2x in front as a common factor, and then we have 1 plus 2x in the parentheses. So now we see that e to power 2x is always positive for all values of x. It's always, always, always positive. All real values of x. Any value of x, we are always, it's always positive. Now, what can change? Of course, the sign of the derivative is the parentheses, but this is only about increase, decrease. We now still need to have a look at the inflection point. We need that second derivative to find the inflection point. So we do the differentiation one more time. Again, let's use the quotient rule. So we have e to power 2x differentiated is 2. E to power 2x times 1 plus 2x without derivative plus e to power 2x differentiated times the second factor, parentheses, differentiated, that's simply 2. So now we see that we can take 2 e to power 2x outside as the common factor, and inside we have 1 plus 2x plus 1, because this whole factor is taken outside. So now we can see that it's 4 e to power 2x times x plus 1, because in parentheses we have 2x plus 2. Of course, we can take this other 2 also outside in front. So we say still this factor e to power 2x is positive. That's something we have to remember for whenever we deal with any derivatives. Let's remember that e to any power is always positive. So this means that the sign of the second derivative is only determined by the second factor, and it has only one critical point. Sign diagram is mandatory. I repeat, it is required. If you don't do it in the test, I will not accept your solution, because I know your tricks perfectly well. And so if x is greater than -1, then the second derivative is positive. If it's less than -1, then the second derivative is negative. So the function is concave down and concave up. So we see, yes, -1 is indeed.
Can you please tell it one more?
What?
The graph.
Which graph?
One more, please.
You don't have a graph.
Right now the
diagram, the sign diagram is this. We have been discussing it in the last 2 lectures. This is required whenever you do investigation of a function using the first and the second derivative. The sign diagram like this is required, as it was explained and demonstrated in last 2 lectures today, and also in your lecture transcript. So please pay attention. And now, so inflection point, and we generally want to see both coordinates, because otherwise the inflection point does not have much meaning. It doesn't make much sense if we don't look at it on the graph. So basically, for inflection points, we determine both coordinates. Please remember that f of -1 is found, the second coordinate, of course, is found from the function, not from the derivative, but from the function. So it would be -1 times e to the power -2 plus 1. So this means it's 1 minus 1 over e square, or you can write e square minus 1 divided by e square. That would be the second coordinate. Yes, that would be the second coordinate, e square minus 1 divided by e square. This sign diagram. So we will go on. You will still have time to catch up and to see what you are supposed to do in the sign diagram. That's clear. Basically, we also mark specifically that at this critical point, at -1, the second derivative is 0, because sometimes the derivative at critical points is not 0, but simply does not exist. So in that case, we should definitely mark that the second or the first, whichever we are using, does not exist. Again, finding the inflection point or points, however many they are. Again, so f derivative, the derivative of this function, it is the exercise 1f from your lecture transcript 6.02. These are, if I give exercise numbers, it means they are from the lecture transcript. So now let's differentiate. X cubed derivative is 3x squared times ln x, not differentiated, plus x cubed, not differentiated, times ln x, yes, differentiated. And of course, derivative is 0. So we see that we have 3x squared ln x plus simply x squared, which can be taken out of parentheses or maybe sometimes not. All right. Okay, it's doing something not very nice. All right, let's take the eraser and okay, there we are. Microphone off, please. Microphone off, please. Microphone. Okay. Oh, I need to waste time checking who has the microphone open. Who is the one having the microphone open? Let me see. Oh, I see. Mr. Patel, you have microphone open. Are you there? Or is it only your name? Mr. Patel. Mr. Patel, switch off your microphone. Are you there? Okay, evidently he is not here, so he will count anyone nearby. This lecture counts as absent for him. I have had enough of people who sign in and then just leave. 3 ln x plus 1. So we simplify the first derivative. Now we can differentiate one more time. Or we can differentiate it taken separately. So the second derivative would be 2x, that's differentiated, times 3 ln x plus 1, not differentiated, plus x squared differentiated, times 3 over x as the derivative of 3 ln x. And so we have 6x ln x plus 2x plus 3x. So we see that now we can take simply x out of parentheses and we have 6 ln x plus 5. So we might have two critical points here as we see. First of all, let's remember that the domain of this function is only the positive numbers. Only positive numbers, that is from zero to positive infinity. And so let's see, the critical points might be 0, but it's not a critical point because it does not belong to the domain. So we will be able to ignore that one. That definitely cannot be an inflection point. So of course x is positive, always positive, and 6 ln x plus 5 equal to 0 to determine the critical points. That means that ln of x is minus 5 over 6, and the actual critical point is evidently e to the power minus 5 over 6. Or you can say it's 1 1 divided by 6th root of e to the 5th power. So this is an inflection point we can check because we understand what is going on with the sign diagram, with the signs. So second derivative, we start from 0. So basically, x is positive. This first factor, this will not affect the sign of the derivative in any way because we are only considering the domain, only the positive values of x. So we have some values. So this is our critical point. I will say x critical point at this point. And we see when x becomes greater, remember logarithmic function. The logarithmic function is increasing. So if the derivative is 0 at this point, 1 over 6th root of e to the 5th, ln increases, which means for greater values of x, these parentheses are, of course, positive, greater than 0. And to the left, where x is less than this value, we know that natural logarithm, as it is an increasing function to the left, it's less than 0. So we see that this function again has exactly one critical point, one inflection point, because you see the concavity directions change. And here the second derivative was equal to 0. So the concavity directions change. So this is actually an inflection point, or the inflection point, one and only, of this graph. It would be rather difficult to evaluate the function value exactly. However, well, it would be possible to at least write something for this. It would be possible to write something for this. Not such a very big problem to write an expression describing the x value. So the inflection point is at this x value, because that's where the direction of concavity changes. All right, now we will have some graphs, some properties of functions. So an example of a graph, this is a practice exercise, actually. It's not really something that is given in exams or tests. So a segment AB, and we have some information about this function. So obviously it's an example of graph. It's not the one and only correct sketch, because you can in principle sketch anything. Like this. Okay. As to the question, somebody said I can also mute him. I did. I only wanted to check how long should I call for him without him paying attention. I was actually checking on him whether he is present really, or is it only his name? That's the thing. All right. So we see, suppose this is A and this is B. Nobody said that A and B both have to be positive, but no problem. We have to sketch an example. All right, the function itself, as we see, is positive. It means it will be above x-axis, right? Next, first derivative is positive. It means the function graph is going upwards. That is, at A, the function value is less, and at B, the function value is greater. So this is from the fact that the first derivative is positive. The second derivative is negative. Remember what that meant? That meant that we had a sad face, negative feelings, or everything is spilling out of the dish if we turn it this way. Negative, losing things. So this means that the function is increasing and concave down. So the sketch will look something like this, increasing but concave down. The curvature, the concavity could be stronger, could be a bit flatter. It depends how well we can actually sketch it. But the idea is, so we can combine these two ideas, increasing, and at the same time concave down. So these two derivatives give us that information. This will be very important later. Next example, still positive. But now the first derivative is negative and the second derivative is positive. Again, we can sketch some system of coordinates, some A and B, positive y values that is above the x-axis. It doesn't say whether we have to do this in the first or the second quadrant, so it's just an example. Now, the first derivative tells us that the function must be decreasing because the first derivative is negative. The second derivative is positive, that means the function is happy, and that means concave up. So, all right, I have to find a decreasing function, for example, like this. It goes down. It cannot stay still. It cannot change the direction. And the concavity up means that, yes, it is going down, 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 but with a concavity up, like this. So this would be the shape of graph on a segment where the function is decreasing and concave up. Now you can guess the other two combinations, right? So if the first derivative is positive, second derivative also positive, in this case, function is negative. So it's actually a little bit of practice for what we will be doing later. Negative, this means that I have to go below A, B, I have to go below x-axis. The function is negative. First derivative is positive, means the function is increasing, so the function value at A is less than function value at B, clearly. And then second order derivative is positive, means this is the happy graph, the happy shape, concave up. And so I go increasing and keeping concave up. So the fragment of graph would be like this. Again, it could be the curvature, the concavity could be stronger, of course. It could be stronger, it could be flatter. So it's not that we always can see it very clearly from function values, because if the function values are such that they seem almost to be on the same line, it's very difficult to tell. So basically, that's one reason why we may investigate the second order derivative. And the next one, again, positive function. Okay, all right, the function is positive, A, B, X, Y. And now the function is positive, first derivative negative, so that means the function should be decreasing. That means up there and down, decreasing. And the second order derivative negative means we have the sad function, so concave down. So concave down, but decreasing all the time. Again, the curve could be stronger. It could be more curly, more curved, but that's not always the thing. So basically, you see there are all the possible combinations, both derivatives positive, both derivatives negative, that was C and D, and then first positive, second negative, first negative, second positive. All possible combinations of signs. This means that any continuous function, any graph of a continuous function basically consists of segments of these shapes. The segments have approximately these shapes. Nothing else is actually possible because nothing else with the signs of derivatives can happen. Of course, we have these things with stronger, smaller curving, flatter, or more shapely. But the thing is that the basic shapes, these four are all that there is. Yes, of course, it could be more strongly curved. It could be curved so that it's almost flat, almost a straight line, and very difficult to notice these things. That's all possible, but the basic shapes are only four. So on each segment of the domain, you should be able to see what happens with the graph, how you should sketch the graph if you know the signs of derivatives. We will use that for investigation and graphing of the functions. Now, the second derivative test for extremum points. So this has been already mentioned a couple of times, last time, definitely on Friday and on Wednesday. So sometimes we determine the minimum maximum nature from the first derivative. And remember what that meant. It's not about this example. The first derivative, we decided, we found the critical values of the first derivative, the critical points. So x1, x2, where the first derivative is 0, or maybe does not exist, is not defined. Sometimes when the first derivative requires division by 0, we have a second kind of critical point where if the, or so it could be or not defined, maybe not defined, that's what we saw last time. Then we determine the signs. Then we determine the signs of the first derivative. That happens exactly in the same way as we solve inequalities using the method of critical values and intervals. And most of lazy people still haven't learned that, even though we discussed it in elementary mathematics. They still keep throwing back some nonsense at me. So the idea of method of intervals, the whole idea of method of intervals for inequalities is you find the critical points of the expression, and then on each segment, when all critical points are marked, on each segment, the expression does not change sign. Only at these points, the derivative, or basically any expression, can change its mark only at the critical points, which means that you can check the signs of the derivative so from any point from inside of the segment. For example, like this. For example, like this. And so the function you could determine increases, decreases. Okay, so this is a maximum point, as we can see. This is nothing. This is nothing. This is neither minimum nor maximum point. So that was one possibility. We investigate the signs of the first derivative. That's the first derivative test for the extremum points using the signs of the first derivative. However, last time on Friday, we saw that it's also possible to use the second derivative, but that only works for stationary points. Again, only for stationary points. So if the first derivative at some point is 0, so you find those critical points of first kind. If the derivative is not defined, this method will not work. Only when the first derivative is 0. So at this point, if the second derivative is positive, that means, so horizontal tangent and second derivative positive, a happy function. So we see that this must be, C is a minimum point. If the second order derivative was negative, evidently horizontal tangent line, this means horizontal tangent line, the graph is curved downwards, concave down, so this means this can only be a maximum point. That is, you may choose whichever test you like, first derivative test or second derivative test. The thing is that sometimes it is easier to use one and sometimes it is easier to use the other. But there's a problem with this, so this does not work. This does not work if the first derivative is not defined at this point. So it might be the spiky critical point, but definitely not a horizontal tangent line. Or if second derivative is 0, because in this case, the question remains open. As I said, the question remains open. because this method, this second derivative test, does not give us any answer in this case. So basically, if you get the second derivative also equal to 0, if both derivatives are 0, then you have to go back and check the signs of the first derivative, because this method will simply not give us an answer. It's not that the answer does not exist. Of course, there is an answer. It's just that this method will not help. We have to go back to this. So there are basically two main tests, first derivative test and second derivative test for extremum points. Remember, please, that the critical points, in this case, critical points always come from the first derivative. The critical points always are determined by the first derivative. So they are critical for the first derivative. The first derivative determines potential or possible extremum points. Second derivative only checks what happens at those points. Or the critical points of the second derivative could be inflection points, but that's a different story. It's something completely different, something else. And because we did the previous one already in class, this function was done in class on Friday. This was, I believe, also done, I think, or maybe not. I guess not. No, we didn't have that much time, I think. So let's do this. So let's use the second derivative test. Okay, my connection is shaky a little bit. Okay, let's use the second derivative test. So we do the first derivative. It is x cubed plus 3x squared. That means x squared times x plus 3, the derivative, the first derivative. So we see that the stationary points are x is 0 and x is minus 3, two of them. X is 0, x is minus 3. These are possible extremum points. Possible minimum or maximum points. Not necessarily, but possibly, they might be minimum maximum points. Now let's do the second derivative. The second derivative, of course, it's easiest to do using this open form of the first derivative. So it is 3x squared plus 6x. That is 3x times x plus 2. Now we have two critical points for this, but it's of no interest for us because we will need to check the value, the sign of second derivative at these points. We are not interested at the moment. We are not interested in inflection points. We are not interested in inflection points at this moment. So what we do, let me see, just one moment. Just one moment, 40, and there we have how many, doesn't say, doesn't look too many. Okay, we'll finish this. So these are possible inflection, possible extremum points. As I said, we are not interested in inflection points. We are not looking at these two, at 0 and minus 2. It's of no interest for us. So we are simply having a look at second derivative at 0. From this, we see that the second derivative is also 0. So the second derivative test does not give us an answer about the point 0. We have no idea what happens there at the moment. This second derivative at minus 3, yes, we are taking the critical points, I repeat, from the first derivative. We check the second derivative at these points. So it will be minus 9 times minus 1, that is greater than 0. This means that x minus 3 is actually a greater than 0. So the shape is this. You can remember the shape is this. So this is a minimum point. This is a minimum point. Minus 3 is a minimum point for this function. But about x is 0, we still have no idea whether this is a minimum or a maximum point. So for this, you see, this method does not give us an answer because the second derivative at this critical point of first derivative is also a critical point of the second derivative. So this is a problem, which means I have to go back to the signs, have to investigate what happens to the right and to the left of 0 with the first derivative. Unfortunately, have to go back to the first derivative, checking the first derivative. Again, this is not something I like. Okay, let's erase. Okay. So at 0, I see that if x is very small positive, very small positive, then x squared is positive and x plus 3 is also positive, close to 0, positive. If x is small negative, then the square is positive and small negative plus 3 is also positive. So we see that the first derivative does not change the sign, that the function sign diagram, looking at the sign, okay, I see every time when my tablet loses connection, we have this problem. So we see that the derivative is, it's positive and it's positive. So the function is increasing, it doesn't change the direction. It's not an extremum point. So x is 0 is not an extremum point, but it could be minimum or maximum depending on the size of the first derivative. So in this example, I repeat what I have been doing here. So first of all, we determined, okay, it's doing it again. We determined the critical points from the first derivative. Extremum points always come from the first derivative. Then we find the second derivative and evaluate the second derivative at those critical points, at those stationary points. And then the sign tells us what kind of stationary point it is, unless the second derivative is also 0. So that creates problems. For in this case, you have to think differently. The second derivative test will not work. Another one, let's see. Okay, one last thing. All right, one last thing. And then we'll do something else. So the first, okay, why does it do it? Slightly problematic, yes. Okay, so the first derivative of this is chain rule, remember, e to power whatever is, the derivative is e to power the same, minus 2x, times the derivative of the u function, the derivative of the exponent, that is minus 2x. That's the first derivative. We see that the critical point, or stationary point, in this case, stationary point, where the derivative is microphone. Sufyan, microphone, please. Sufyan. I will shout. I will shout because I need to test whether you are actually there and listening. I've had enough. So the stationary point is 0 if only x is 0. Why is that? Because e to any power is always 0. Exponential function e to whatever power is always positive, sorry, not 0, for all values of x, any real values of x. So there's one stationary point, it's the critical point, and now I want to know whether this is a minimum or maximum point or something. So what we do with the second derivative is we differentiate this function again. Now we have a product rule, derivative of e to power minus x squared is still the same, minus 2x e to power minus x squared times minus 2x without derivative, plus minus 2 is the derivative of 2x, and e to power minus x squared doesn't change. So the product rule in this case, we have, what do we have? We have, for example, 2e to the power minus x squared as a factor outside the parentheses. And in the parentheses, we now see we have minus 2 times minus 2 is 4, so 2 still stays inside, of course. X, okay, I did it again. Sorry. This is rather annoying. So we have 2x squared minus 1. If I bring out 2e to the power x minus x squared, we have 2x squared minus 1 inside the parentheses. That's so that it's easier to find, to evaluate the second derivative. Now, the second derivative at 0, we are checking, we are using this second. We are using the second derivative rule, the second derivative test, and I need to go back and go forth. In order to manage this, the second order derivative at 0 is 2e to the 0 power times 0 minus 1. We know that e to the 0 power is 1, so it's 2 times minus 1, it's negative, which means that x is 0, which means that, okay, now this is, I'm sorry. This means that the point x okay. All right, my tablet is trying to give up on me. So x is 0 is a maximum point. And we can actually find the maximum of the function. If x is 0, then e to power 0 is 1. So this would be the point on the graph. So this is how we can use the second order derivative. But as we see, not really always. Now, looking at the sad experience from last time, I will be doing this. And now please sign your name one more time. Sign attendance one more time, please. Everybody who is listening, everybody who is present. I'm giving you 1 minute for that. Because honestly, the things I saw last time were rather sad. Okay, thank you. Okay, I repeat, this is the moment where you can sign one more time, or actually you should sign one more time, because I really want to see who is staying and who is listening. I know that there are people who switch on, sign in, and go do something else. That's nothing new. Nothing new under the sun. All right, looks like this is it. Okay, I will do another line. So, somebody woke up. Who told you that you have to sign? Okay, never mind. Another line. Not a problem. Okay, so now all this, both the derivatives and other things, that are necessary to graph the function, I might say it's still not quite enough. You can find the inflection points, you can find out the shape of graph, but the graph, if we want the graph to be accurate, we still need something else. And today we start with finding asymptotes, and that is really the very last thing that we need for graphing the function. So we will discuss horizontal, vertical, slant asymptotes, and we will see the overall plan of investigation, how to investigate a function, the general big plan. This big plan is what you will have to follow in order to finish, to complete your home assignment. So far, you already know how to work with the functions that you have for your home assignment, and the home assignment is has long been published from last week. You can already investigate the first derivative, increase, decrease, the second derivative, concave up, concave down, inflection points, minimum, maximum points, but that is still not enough. So there's some more information that is necessary, and of course, the overall plan of action, according to which you can basically take an A4 format paper, start from the beginning, write down everything that is required, and basically in the end you have absolutely enough information to sketch the graph quite accurately, by the way. Okay, so there we go. The asymptotes of a graph, what are those? So first of all, from Greek language, the asymptote, the word asymptote means not falling together, not falling together. Not falling together in the sense that it doesn't really join the graph. An asymptote is a straight line that actually, the graph is approaching. So the asymptotes could be, for example, horizontal. If you remember, for instance, if you remember the arctangent. Remember, the graph of the arctangent went like this. I am using familiar graphs so that you have an idea. Remember, this was pi half, this was negative pi half. So basically what we see is that the graph of arctangent infinitely approaches the horizontal line pi half in the positive infinity, where x is positive infinity, goes to positive infinity, and negative pi half when x tends to negative infinity. We saw this when we were discussing the inverse trigonometric functions and their graphs. So this is something already somewhat familiar. You know that sometimes the graph, the range of the function is so limited that the function doesn't go out, and in very special cases, it actually doesn't reach that limit. It doesn't actually reach the limit. When x tends to infinity, the tangent, the arctangent, goes closer and closer and closer to pi half, but it never actually reaches it. So this is the idea of not falling together, never really reaches it. Or we could have, for example, you might remember the logarithmic function. So if this is number 1, remember the shape of the graph of the logarithmic function. For instance, it could be the function ln of x. So of course, this was smoother. This is somewhat shaky, my hand at the moment. So we see that because logarithm is defined only for positive x values, as x approaches 0, you see that the graph tends to negative infinity, which means the y-axis is again that line that the graph is approaching but never really reaching. So this is a vertical line. So we see we can have horizontal line that the graph is approaching. We see that there might be a vertical line that as we go to infinity down, the graph approaches this vertical line. And there could, of course, be something quite completely different. For instance, something like let's see, a line like this. I am not going to give you any function, not going to give you any formula, but for instance, it is possible to have a graph something like this that has some curving here. Well, in the near region, near neighborhood of the origin, for example, but as the x values increase, the graph could approach also a slant line. It doesn't have to be horizontal, it doesn't have to be vertical, as in logarithm case, this is vertical, see? But it could be slant. So 3 different kinds of asymptotes. The line is called an asymptote. And what this actually means, it means that in infinity, that is, when we approach infinity, well, we cannot approach, but when we go off to infinity, far, far away from the origin, then the distance between the graph and the asymptote, the line, asymptote is a line in principle, a line. In the infinity, the distance between graph and asymptote tends to 0. Of course, the graph approaches the asymptote. Now, the big question is, can we actually see what the asymptotes are just from the equation? Because our purpose is to investigate the function so that at some point we can draw that graph, so that at some point we can sketch and understand the function perfectly. And for that purpose, we need to establish asymptotes not from the graph, but from the equation. And so we start with the simplest case, the horizontal asymptote, as we saw. So basically what we saw already, we could say that if if x tends to infinity, then the function value tends to a certain value. Remember that remember the arctangent. When x goes to infinity, the function value tends to become pi half. So in principle, let me please remind you that what this means is that the equation of the line, this is an equation of a line, y equals b is an equation of a line. An asymptote is a line. So what I sometimes see, what people do, is that they write, oh, 3 is an asymptote. What? 3 is a number. So if you want to give me asymptotes, you have to write the equation of a line, not just number. You cannot say the horizontal asymptote is pi over 2. No, pi over 2 is a number. So you be very careful when you need to write down the asymptotes, you have to write the equation. For example, the function 1 over x squared, we could actually think, let's say, we could think of graphs, for instance, but on the other hand, we can understand that the limit of 1 over x squared, when x tends to positive or negative infinity, we do understand that the limit is 0. When x tends to infinity, the limit is 0, no matter what, which means y is 0, that is, the x-axis is the horizontal asymptote. So this is the horizontal asymptote for this graph. Horizontal asymptote, y equals 0. The x-axis is the horizontal asymptote. Now we can actually imagine the sketch. When x is 0, the function is not defined. For very small x values, the function value is large. For very large x values, the function, of course, becomes small. And because this is an even function, it means the graph is symmetrical, of course. Okay, my sketching for symmetrical graph is rather off, but the graph is symmetrical because the function is even. So again, you see that this kind of information, even odd asymptotes, give us additional information about the function and actually make it easier to sketch the graph, to understand what's going on. So we look at this and we say, all right, the horizontal asymptote is the line y equals 0. Another function, g of x is 2 to power x minus 3. Remember the shifting of the graphs. So generally the function y equals 2 to power x intersects the y-axis at the point y equals 1. But if we have to subtract 3, do you remember what happened to this graph? It has to move 3 units down. So I could say, all right, 1, 2, 3. So generally, the exponential function would have the asymptote, the x-axis, but because we have to move it 3 units down, 3 units down, so the horizontal asymptote now, is minus 3. So we have moved the graph 3 units down. If x is 1, then we have minus 1, so it would go something like this. And if we have a look at the limit, so the limit when x tends to only to minus infinity, in this case we see, when x tends to minus infinity, 2 to the minus infinity is 0, so it's minus 3. So the horizontal asymptote is y equals minus 3. We can do it using the limit, but I illustrated using our knowledge about exponential functions. When x tends, so sometimes you see the horizontal asymptote could be only in one direction, only for x tending to negative infinity or only to positive infinity, only on one side. It could be the same on both sides as for this function. And of course, in the previous slide, we had the arctangent function for which actually we have one horizontal asymptote when x tends to plus infinity and another horizontal asymptote when x tends to minus infinity. So all these possibilities can happen. So this is where we have the horizontal asymptote. That's very simple. Simply have a look at x tends to infinity. What happens to the function? If it has a limit that is a number, then that number actually gives you the horizontal asymptote. The equation y equals that number is the equation of the horizontal asymptote. In this case, it's y equals minus 3. In the first example here, it was y equals 0. Now, okay, I forgot that I already had my coordinates. All right. Now, the vertical asymptote. Again, it's a line, equation of a line, x equals some number a is a vertical asymptote. Let's see what might happen. So basically, in our previous example, we had this y equals 1 divided by x squared. 1 divided by x squared. So basically, you see, we had the horizontal asymptote, but we see very clearly, we can see there's also the vertical asymptote. X is 0 is a vertical asymptote. So when does that happen? Evidently, when the function is not defined at x, when the function is not defined at x, this is when it happens. And basically, we can talk about the discontinuities of type 2. Remember, type 2 discontinuity when the one-sided limit is infinity, positive or negative. So we can have the right-hand side limit from the right, positive or negative infinity. So whether the graph is going up or down, or we could have the left-hand side limit, positive or negative infinity. So sometimes the asymptote is really one-sided. Remember a logarithmic function? The y-axis was the asymptote as x approaches 0 from the right, the first kind. So for the logarithmic function, For the logarithmic function, for that example, we had limit when x tends to 0 plus 0 from the right-hand side of ln x is negative infinity. And so in that example, the y-axis, x is 0, was the vertical asymptote. Vertical asymptote, x is 0. That was in the example at the beginning. So that was for the logarithmic function. That was for the logarithmic function from the previous slide. Oh, well, before that. Logarithmic function has a vertical asymptote. We can check it like this. Check the one-sided limit, the correct one-sided limit. They don't always exist, of course, so it's not always it's not always something with an asymptote, but let's now check something that exists. Tangent. Okay, if we have the tangent function, remember that tangent is not defined for those very same values, in this case of x. Remember the tangent function, that was the arctangent previously. Now this is the tangent function. We know very well what the tangent graph looks like. Well, I do hope that you know very well what the tangent graph looks like. Of course, the tangent graph looks like this. And so we see that we could take the one-sided limits, for example, at pi half, and we know that evidently the period repeats. So basically, when we approach pi half plus from the right-hand side, the limit of tangent is minus infinity. It tends to negative infinity. If we approach this very same value of x from the left, then the limit is plus infinity. So in either case, so this vertical asymptote works for the period of tangent function on the left, and it works for the tangent function for the period, for the piece on the right. This is an accurate sketch. I'm using this opportunity to demonstrate. Well, I didn't want to demonstrate this, but see how my function turns away from the asymptote. It's not correct. It should be approaching, approaching, approaching. It shouldn't be turning away. It is never turning away from the asymptote as it goes on. So for the tangent function, we have this kind of a function, or if you like, the function 1 over x. 1 over x, remember that's actually the inverse variation or inverse proportion, and the graph is a type of hyperbola, a specific type of hyperbola, as you might remember. So I will take this way there. So the graph is a hyperbola like this. And you see that, yes, again, from the left, when we approach 0, so x tends to 0, from the right, 1 over x stays positive, it's plus infinity, and the other one-sided limit, I'm reminding you, x tends to 0, minus 0, so from the left, like this, we see the function goes to negative infinity, of course. And we already discussed these one-sided limits or similar one-sided limits in the limits section in the 4th unit. So that was the reason for us to understand the behavior of the function. Limits can be used very effectively. And finally, the slant asymptote. Now that's something worth discussing seriously. The slant asymptote. So now we are there. Okay, this slant asymptote. Let's see. Okay, the slant asymptote. First of all, how do we understand the difference, the distance from the graph and the slant asymptote, this curve? I thought I had, yeah, I thought I had this graph. All right, so basically it's the vertical distance. By definition, we can say when x tends to positive or to negative infinity, the rest is the same, the difference, see, the slant asymptote, of course, it's a line, and we can write the line in slope-intercept form, so perhaps. And then what does that mean? What does that mean? The graph of the function approaches the line infinitely close. It basically can mean the distance. We could measure the distance, let's say, with a perpendicular, but basically in this case, it's sufficient that we measure the distance for every value of x. We measure the distance vertically between the function value, this function value, and the y value of this asymptote, of this straight line. So basically we are checking for this. We are checking for this. If a slant line or any line given by this equation is an asymptote, that means the difference between the function and the line value, this linear function value, tends to 0. The limit of this difference is 0. So this is how we define the slant asymptote. Now, the big question is, all right, that presumes that we already know kx and b. We already know what k and what b are. So how do we find these values? That's another question. And I would say an important one. So how do we find these values, k and b? This means that we have already found them and put them into this limit. So this doesn't work for finding it. It doesn't work for finding it. It only works as a definition. But how to find the slant asymptote, that's what we will do next. All right, I will not do this. Okay, so finding slant asymptote. What we do is we remember, okay, there is this formula, and no, we don't have to remember anything. The formula is this: the coefficient k is found. The coefficient k is found by divide the function by x and let x tend to infinity. If this limit exists and is a number, then it is the coefficient k for the slant asymptote. Why is that? I will do a very, let's say, rough thing. This will be, let's say, not mathematically quite polite. This is not mathematically, let's say, perfect writing. But you might have an idea. So if the function f of x tends to kx plus b, difference tends to 0. So I would say the value of the function approaches the value of this kx plus b. So what we do, if x tends to infinity, in this case, let's divide both sides by x. What happens when we divide both sides by x? The function value divided by x tends to k plus b divided by x. Because b has to be a constant, this means that this particular term tends to 0. So this particular term tends to 0, which means that this quotient, function divided by x, actually approaches k. So this is, let's say, mathematically not very nicely written, not mathematically perfectly correct, but that's an explanation for this formula. How to find k, take the function, divide by x, and let x tend to positive and or negative infinity. It might be different for different functions. And then to find b, we subtract this, because again, from this part, if I subtract kx from both sides, function minus kx, it must tend to the value b. This difference will tend to b. So again, very simple to explain why. Why do we find k using this limit, and why we find b using this limit? Also, I would like you to notice that In the first limit, yes, we divide the function by x. In the second limit, the function is not divided by x, but we subtract k found in the previous step multiplied by x. So if both these values are real numbers, if k and b are both real numbers, then y equals kx plus b is the slant asymptote. Y equals kx plus b. If one of them, if even one of them is not, if even one of them is not a real number but infinity, or sometimes one of these limits does not exist, then the asymptote does not exist. Sometimes you already see that k is not a real number. Leo, switch off the microphone, please. Leo, do you hear me, Leo? No, he doesn't. Okay, counts as absent.
Yes, ma'am.
Okay, so sometimes it happens this way, that k is a number. So sometimes the k limit doesn't exist, and then we say there's no slant asymptote. Sometimes k is a number, but f of x minus kx is not. Sometimes it happens, I've seen it happen, and that means that the asymptote still does not exist. The asymptote still does not exist. There's no asymptote. So both numbers must be real numbers and they must exist. There's also another interesting situation. When k is 0, it happens. If k is 0, that means that the line is horizontal. Then we have y equals b. Then we have y equals b, right? If k is 0, that means that horizontal asymptote is only a special case for slant asymptote. So in many cases, people simply find the slant asymptote, and if the k is 0, then they understand, of course, this means that the asymptote is horizontal. The slant asymptote is actually horizontal. So basically, it actually saves you some time, it saves you some work if you only find the slant asymptote and not the horizontal, because of course the slant asymptote can degenerate, the slant asymptote can actually become horizontal for some functions. It's not slant really, it's actually horizontal. However, there are many situations where you look at the function and you know clearly that why make all this fuss with slant asymptote, that I can see that there will be a horizontal asymptote. That is, in the situation where you clearly see that the limit of the function, when it approaches, when x goes to infinity, is a number. So sometimes the horizontal asymptote actually is easier to find because it's very obvious. In that case, of course, we don't bother with slant asymptote. You should understand, I hope, that a function cannot approach a slant line at the same time as a horizontal line. So of course, it's either slant or horizontal, or maybe neither, but never both on one side. Yes, it could be horizontal on the left and slant on the right, but that's different. So in principle, you may just start with a slant asymptote, and then in some cases, it might become horizontal if k is 0. In some situations, you'll see already, oh, we will have a horizontal asymptote. Let's not bother with a slant. Let's find the limit of the function, and that's it. We have found the horizontal asymptote. So it takes some thinking, never something mechanical, never some mechanical copying and random equations that you tend to write sometimes. So it's sufficient to find the vertical asymptote, which is generally at the discontinuity points. The vertical asymptote generally happens at discontinuities type 2. Type 2 discontinuity. And the slant asymptote is enough if it turns out to be horizontal, very good. But If you are clever enough and you see already that it should be horizontal, you can start with the horizontal. It's shorter, it's faster. If you are mistaken though, and you thought it would have a horizontal asymptote, but it does not, then you have, of course, more work to do. But it's up to you which you choose. Examples. So the first example, what are the asymptotes of this graph? I am not going to sketch the graph, but I am going to think about the asymptotes. I am going to think about the asymptotes. So let's see the discontinuity. We see that for the domain of this function, x cannot be equal to 1. And therefore, I would say it has a vertical asymptote x is 1. Because if x tends to 1, we see that the denominator tends to 0, and that means that the function value actually tends to infinity. It's very clear that the vertical asymptote is x is 1. For these rational functions, it is generally very clear. Do you think it would have a slant asymptote or horizontal? Can we save ourselves some work? If we do the wrong thing, then we have made more work for us. So I would say, because see the highest power, the degree of the denominator is the same as the degree of the numerator. We only have x and x. We can even see that the limit when x tends to infinity will be a constant limit when x tends to infinity of 3x minus 4 divided by 1 minus x. Remember what we did? We divided out x, and then we had 3 minus 4 over x. We had 1 over x minus 1 as we divide out x. And so we see when x tends to infinity, then these elements, number divided by x, number divided by x, they both tend to 0, of course. So the limit of the function is 3 over minus 1. That's minus 3. So we have the horizontal asymptote, x is negative 3. And that's it. There will be no slant asymptote because it has horizontal asymptote. Horizontal asymptote is simply a special case of slant asymptotes. So you don't have to think about slant asymptotes anymore. So no slant asymptote, that's clear immediately. And that's it. Another example, we start with the domain to see x squared minus 3x cannot be 0. That is x times x minus 3, yeah, right? So x cannot be 0 and x cannot be 3. So we have two vertical asymptotes. These are the points of discontinuity. For rational functions, the discontinuities and the vertical asymptotes are so easy to find. It's harder, it's more difficult for functions that are not algebraic, not rational, for functions that contain, for example, radicals, for functions that contain logarithms, tangents, exponential functions, it's harder. But for the rational functions, it's sufficient to determine the discontinuity of the function, the 2 points in this case. So we would say we have two vertical asymptotes, x is 0 and x is 3. Two vertical asymptotes. Now, do we have a horizontal asymptote or slant? That's a good question. If we look at this function, we see actually that we do not have the same exponent. The degree of the numerator is greater than the degree of the denominator. This means that there's no horizontal asymptote. It's not a number. The limit will not be a number. Whether we can find the k value, whether a slant asymptote exists, that's still a question. But I understand because these numbers, 3 is greater than 2. the exponent 3 is greater than exponent 2, this tells me that there's no horizontal asymptote. This tells me that there's no horizontal asymptote. So to find the slant asymptote, for slant asymptote, y equals kx plus b plus, that was, let's see, k, if it exists, then k is the limit when x tends to some infinity of x cubed plus 2 divided by x squared minus 3x. And this is the reason why in the first elementary mathematics test, you had to establish the expression f of x divided by x. We needed to practice this. So if I divide by x, it means I multiply by 1 over x, which means the denominator becomes also cubic. Limit when x tends to infinity of x cubed plus 2 divided by x cubed minus 3x squared. Very, very careful when you divide by x. And so again, when we take out the x cubed, divide everything by x cubed, I will divide directly without writing it in front. We will have 1 plus 2 divided by x cubed, and we will have 1 minus 3 over x. If I divide out x cubed, infinity, that's infinity. So we see that again, these fractions tend to 0. 1 divided by 1 is 1. 1 divided by 1 is 1. So k is 1. Very nice. We will have a slant asymptote, hopefully, if we can find b. So this is the first thing we did. Now the second thing is find b. b would be the limit when x tends to infinity, function minus kx. Function is x cubed plus 2 divided by x squared minus 3x without division by x. Not this, but the given function minus kx. K is 1, so minus 1x. Because k is 1, we just found it. I will actually mark it with some color. So because we just found k is 1, this means I have to write k is 1 here in front of x. So let's now bring these on the same denominator. So x squared minus 3x. We have x cubed plus 2 minus, now x to bring on the same denominator must be multiplied by this expression. So x times x squared minus 3x. We will see x cubed minus x cubed will disappear after opening the parentheses. So we have limit when x tends to infinity. We have 2 plus 3x squared, looks like, yeah, divided by x squared minus 3x. If we divide out x squared now, or if you prefer L'Hopital's rule, actually, these functions can be easily, of course, infinity divided by infinity, can be easily, the limits can now be easily found using L'Hopital's rule, if you prefer that one. You would still need to differentiate twice. So you would have, evidently, dividing out x squared, you have 3 over 1, so that limit is 3. So we see that b is 3. And that, taken together with k, means that the slant asymptote is y equals kx plus 3, that is 1x plus 3. This is the slant asymptote. Yes, you see, it takes some work. Finding those limits takes some work. That's unavoidable. The good news is that if you can use L'Hopital's rule well, if you are, let's say, good at that, you can use L'Hopital's rule, whichever method you like, to establish the values of these limits. That's not a problem now. So to find limits, yes, you may use L'Hopital's rule. 4 minutes remaining. I do believe I will deal with these examples next time, because in the remaining minutes, okay, find the asymptotes, some exercises. Yes, we will do some exercises next time, but I want to give you the overall plan for investigation of functions so that those who are, let's say, who are already working on the homework, you can start putting things together, right? So I know that there are not so many, but a few people, while I do that, I announce the last check. Please write your name one more time. Those who are here and present, my apologies. This is basically, directed against those people who are not. Thank you and sorry. Meanwhile, how to investigate a function? We always start without derivatives. Whatever we can find without derivatives, we do. So the first thing is domain. It means it is important to establish for what x values the function is defined, or in many cases is which are the few forbidden x values. For instance, if you know that the function is defined for all x values except one or two specific x values, you already start thinking, okay, those will be the vertical asymptotes probably. So that's imperative, understanding the domain. So you have to start by looking at the domain. Where is the function defined? Next, if the function is odd or even or periodic, it's good to establish that, because you can use copy paste then. You draw a part of the graph, and if it's odd or even, you do the symmetrical part. If it's periodic, you copy paste the period. You can repeat the function. Well, basically, that's a very good thing. It's for you, because if you don't do this, then you have to look at the whole domain of x, and it might be rather, well, difficult if there are many important points. The next thing is the zeros and y-intercept. That means you do function equals 0. Zeros of the function are the points where the graph will intersect the x-axis. So that would be points on the x-axis. Y-intercept is a point, no more than one, on the y-axis. So for x-axis, for zeros, you do this, solve an equation. For the x-axis, you simply put x is 0 and you find the y-intercept. Those points are very good to start, well, not at the very beginning, but those points are very good to put in the graph. These are the first points that you can mark in the graph. The intersection points with the axis, in other words. These are intersections with axis. Intersections with the axis. So you have maybe nothing, because there are graphs that do not intersect the axis of coordinates. Maybe you have only the intersection point with the y-axis. Maybe you have only the intersection points with the x-axis. Maybe you have the origin, the function passing, the graph passing through the origin. So it's the same point for x and y-axis. All kinds of things are possible there. So this is before we even start with the derivatives. Then asymptotes. Because if you sketch in the asymptotes, of course, maybe with a pencil, if you sketch the graph with a pen, or in a different color, or with a dashed line, that means that you already have, let's say, it's like a handrail for construction. You know that when you walk up or down the staircase, especially if it's narrow or wobbly, or if you walk across a bridge, you like a handrail. So this asymptote is like a handrail for the function. So not to get lost, not to wobble away, the asymptote gives you a frame in which you can actually sketch the graph more accurately. So asymptotes can be found at this point. Asymptotes can be found at the end also, not a problem. The plan is not exactly 1, 2, 3, 4. These are simply the things that should be done. In what order? Well, sometimes we forget the zeros and then, oh, I didn't find the intersections with the axes. So I can do it at the end, no problem, of course. First derivative, everything that follows from the first derivative. This is where you investigate the first derivative of the function, where you sketch the sign diagram with the critical points, where you indicate, where you indicate how the function will behave. It is very good because it gives you more information about this function. And yes, local extrema, that is minimum maximum points. This is something that you should find both coordinates, because as soon as you find this, you can again immediately plot it in the system of coordinates. Plot it immediately, the point, the local extremum point that you find. And then the second derivative and everything that follows from the second derivative. Inflection points, concavity, and then you will be able to put together this kind of information. By the way, in this way, you will be able to find put things together and understand how this graph behaves after you do the second derivative. If you already have the first derivative, so you have a pretty good idea about how the function will behave. And then finally, you have the system of coordinates, you have the asymptotes, you have the interesting points. These points also should be, all of them, they should be marked in the system of coordinates. Using the coordinates, mark them accurately. And then look at those diagrams and asymptotes, and you can sketch the graph. We will do a complete sketch next time on Wednesday, of course. We will have some more, maybe some more asymptotes, but our main attention is going to be on this plan. Sometimes some functions don't need asymptotes. For example, polynomial functions do not need asymptotes. We know that the basic shape of a polynomial function is something like this, perhaps. It does not have any asymptotes. No asymptotes whatsoever, neither the quadratic function, nor the cubic function, nor any other functions with ups and downs and minimum maximum points. They do not have asymptotes, for example. Then there might be some other functions for which asymptotes are very useful, but the second derivative, finding the second derivative is messy. Finding the inflection points is very difficult, so we sometimes skip that part if it doesn't help. And for graphing, of course, you may choose as many additional points as you like. Additional points as needed in the graph. Additional points as needed in the graph. If you don't need any additional points, fine. If you do, then you can plot some extra points to make this graph more precise, more accurate, that's all. All right, so it's time for me to finish because I have a meeting in just a couple of minutes, 5 to be exact, or 4 now. Those who are retaking the unit tests, Unit test 4 at 1:30, that is 1 hour and 40 minutes time to get ready for that. And the Unit 3 test, I hope that's very few people because this is the 4th retake for the 3rd unit. 4th retake. I've done it 3 times. And those of you who have not bothered to do it all these 3 times, well, might get this very last opportunity. And that's it for now. The links for the retakes. So unit test 4 at 1:30, unit test 3 at 2:30. So the links are in Ortus. I will see you in a while, and then there are some people whom I will see also tomorrow, and then there are some people whom I'll see only Wednesday. So goodbye to all those, and I will probably see quite a few of you in an hour and a half for that test number 4. And that's it.